So this video is going to be answering the question, where is oil stored? This is kind of a confusing topic for me when I started in the industry, is that it didn't make sense to me where the oil could be, because I knew that rocks were solid, and I knew the ground was made of rock. So the concept I had of where the oil stored was sort of like a big cup, like there was just an area underground and you dig a hole and there's this vat full of liquid in there. And I think this is perpetuated on a lot of sites. I've seen environmental images where they show the earth crumpling up as oil is produced, and it says like save the lifeblood of the earth or something like that. But removing oil volume does not decrease the height of the ground. It can in more complicated situations, but not by very much. So I know I'm completely stupid and I should have understood how it worked, but for all of you other people who are like me and don't really understand how oil is stored, it's basically like having a jar of marbles. And you can see there's a fluid in there and it can sit in between those spaces. So the equivalent of the marble in our scenario is sand. So if you imagine you start out with a big piece of rock and it starts up in the mountain, and as it comes down a river it breaks into little pieces. By the time it reaches the ocean, it's like you see when you visit the beach, there's all these little pieces of sand. Now, as more and more pieces of sand come on top of it, it gets more and more squished. So they become they don't really become loose like you'd see, but they become really solid. And there's cementing agents, and there's different types of depositional environments, but this is just a good way to imagine it, because all oil is going to be stored in sedimentary deposits, because not only is that where the sand's being deposited, but it's where the little critters are being deposited. It's the little critters, I should say, like algae and plankton, because that's really what we're talking about. It's not animals. But so basically the oil can sit in between these little pieces of grain, and that's where it is. Now, when you look at a rock, it doesn't seem like there could be very much in there, because, I mean, these marbles have huge spaces in between them. So you can imagine, well, yeah, this is a lot of liquid. But the funny thing is, what ends up happening is all that matters is the shape. This may seem very counterintuitive because these grains are large, so they should hold more space in between them. But on the contrary, if I have smaller grains, sure, they have less space in between each area, but there's more of them. And so how you can kind of imagine this is if I was an ant and I was looking at a rock, it would kind of look like a thing of marbles. Well, if I was zoomed out a little bit, it starts to look smaller and smaller. So in a way, it's kind of like the scales just depend on what view you're viewing it at, and it ends up being a matter of geometry. So we can demonstrate this. I have both these jars. I tried to fill them to about the same level, and these are both perfectly spheres, so it's just a matter of their shape. So if you expect the larger one to hold more, it shouldn't overflow in here. But when I fill it up, if I don't spill, you can see it's right at the same water level. So because these were the exact same shape, we can hold the same volume. Now, another problem you can come up with is, well, there is one other factor. So these are all the same shape, which helps, because if you could imagine there being smaller grains in here that could fit in between these gaps, then there's less space that can be held. So if we were to mix the marbles with these little BBs, then we would hold less oil per volume. So actually, I just gave you one of the best scenarios, a perfectly round object. If the objects are not round, like imagine if they were blocks. If they're a solid block, you can imagine them fitting together like Jenga pieces. And that's going to be the lowest energy level. Well, if they're round, there's no way I can take this marble and make it sit flat against the other marble. But if they're flat, if they were like two pieces of paper, I can put them on top of each other and they're flat, and I step the next one and there's no volume in there. So what matters to find the porosity is the shape, the sorting, which is how much of large grains you have versus small grains. Are they all consistent, or are they distributed across the large spectrum? And but the size doesn't matter. So pretty much the best case scenario you can have is this. They're perfectly rounded, they're perfectly sorted, and that's going to give you the maximum volume. And I'm going to do some math on this so you can understand the details, but basically this is going to hold a lot of water, or oil. So if I'm going to pour this in here, that's a lot of liquid. I mean, sure, it's not as high as this level is in the original, but you can hold a lot of oil in the reservoir this way. So even though these are very small, you can actually hold massive volumes, and that's how we get massive amount of oil. Okay, so this is the analytic portion of the video, where I'm going to show what I showed in the demonstration, but in a mathematical approach. And then I'm also going to try to help you understand how we actually calculate porosity. So this is going to be demonstrating the same thing. So imagine we're in 2D space, because you could do it in 3D space. You just do a integral in the z direction. But since we're working with symmetric objects, it doesn't actually matter. So imagine that we have a square reservoir, and there's two of them in the same size. I'm going to say they're 2 by 2. We can say they're inches or feet, or it doesn't really matter the units, as long as they're consistent. So let's go with inch, I guess. So if they're 2 inch by 2 inch, we could have the possibility of having one circle with a 1 inch radius, or we could have 4 circles poorly drawn, but the concept should be all there. That guy's definitely too big. Whatever. So there's and so their diameter would have to be 1/2 inches. Sorry, I mean the radius would have to be 1/2, because then to go 2 across. So in this case scenario, to find the porosity is the free space between the grains divided by the total area. So we can figure out this area, and that area is just pi r squared, and the total area is 2 by 2. So the total area is going to be 2 squared, or we'll just write this generically, length squared minus pi r squared. So if we do this in the actual numbers we had, that becomes 2 squared minus pi times 1 squared, which is pi. So it's 4 minus pi is the area that this is taking up. Therefore, the porosity is going to be this divided by 4. And that's going to give you a percentage. I'll just find the actual percentage so you can kind of get an idea of the scale. So 4 minus pi is approximately 0.85. And then you divide that by 4 by 100. Which is 21%. Right, so this is the free space divided by the total area. And over here there are 4 circles, and each of their areas is pi times 1/2 squared. And we can subtract that by the same area, which is 4. So if you square this ends up being 1/4, and then this is times 4. So what you have is 4 minus pi, and the total area is 4. And that'll give you the same percentage. It's going to be 21%. So 21% of the volume of this rock is going to be held by the is going to be able to hold fluid. And it didn't matter that we used 4 smaller pores or if we used 1 larger pore. And that's how you would generally calculate the porosity. So if you imagine, though, if I filled in this area with a smaller rock, and this area with a smaller rock, and this area with a smaller rock, and this area, and this area, and this area, eventually we have no area left. So what you do in your analysis is you'll crush up a sample of rock, and then you'll find the distribution of the grain sizes, and then from that you can figure out mathematically what the porosity is using a similar process as this. Or the experimental way is to just take a core sample, so you cut a piece of your rock, and then you just put fluid into it and see how much fluid you have left. So I hope that clears up some things about how oil is stored and how you might go about doing a problem with it. If you have any questions or any things that I did wrong, please feel free to comment or message me. I'll replace the video or create a new one. Just let me know what you're interested in. Thanks.